Lewis Structures is part of the Flipped Learning in General Chemistry series. In this video, I'll introduce the Lewis structure, which is the standard format for drawing molecules. It shows both the connectivity between atoms and the location of valence electrons. After completing the assigned problems, you should know the octet rule, understand the parts of a Lewis structure and what they're telling you, and be able to create new Lewis structures from molecular formula. We'll begin with single atoms written as Lewis symbols. Here are some elements from the second row of the periodic table along with their ground state electron configurations. We're interested only in the valence electrons, which in these cases are found in the n=2 shell. Lithium has 1 valence electron, boron has 3, nitrogen has 5, and fluorine has 7. Now, here are the Lewis symbols for these atoms. Each dot represents a valence electron, and the elemental symbol represents the nucleus and the core electrons. A Lewis symbol is a convenient way to show the octet rule, which is the tendency of main group elements to obtain 8 valence electrons. What's so special about 8? It's the number required to fill a valence shell that has both an s and a p subshell, which is the case for most of the main group elements. Elements that form ions do so to achieve an octet. The halogens, for example, all have 7 valence electrons and are commonly found as halide anions after gaining 1 electron to achieve an octet. Lewis symbols are set up to show this. There's room for 8 electrons around the atom, 1 pair on each of the 4 sides. Notice that the charge of the ion is shown in the upper right corner. Elements on the left of the periodic table can achieve an octet by losing their valence electrons. The group 1 elements, like sodium, lose 1 electron to empty their valence shell. Na+ has a noble gas configuration because the n=2 shell is now filled, but we don't show any electrons with this Lewis symbol because the original n=3 valence shell for sodium is empty. Group 2 elements, like calcium, satisfy the octet rule by losing both of their valence electrons to make +2 cations. Lewis structures are diagrams of molecules that show the connectivity of atoms and the distribution of valence electrons. Here's the process for turning the formula H2O into a Lewis structure for water. First, we count the total number of valence electrons in the molecule. Review electron configurations if you need help with this. For water, oxygen contributes 6 electrons and each hydrogen contributes 1, so there should be 8 electrons total in our Lewis structure. Next, we arrange the atoms to show connectivity. I'm going to put O in the middle with an H on either end. This step takes a little chemical intuition to get right. I know, for example, that hydrogen can only make 1 bond, so H can't be in the center. The only possible configuration is with O in the middle and the H's on either side. Now I'm going to connect all the atoms with a single covalent bond. Remember that a covalent bond is a pair of electrons shared between 2 atoms, and this is shown in a Lewis structure as 2 dots drawn between the 2 atoms. Another way to show this is with a single straight line connecting the atoms. These 2 pictures are equivalent, but the line style is more convenient and so is more common. Now I fill in the remaining electrons in an attempt to give each atom an octet. I started with 8 electrons and I only have 4 remaining after making the 2 bonds. I'm going to add them all to the oxygen atom. A pair of electrons not in a bond is called a lone pair or a non-bonding pair. So now, do all the atoms have octets? To answer this question, I have to decide how I'm going to count the bonding electrons. Shared pairs count towards both atoms, so oxygen does have an octet. 2 pairs of bonding electrons and 2 pairs of non-bonding ones. Each hydrogen only has 2 electrons, but that's actually good because hydrogen is an octet rule exception. This is because hydrogen has only an s orbital in its valence shell and so can only hold 2 electrons. So this is the correct Lewis structure for a water molecule. Next, let's try a harder example that has a few additional steps. Nitrate is a polyatomic anion with 4 atoms and a -1 charge. Counting valence electrons, we get 5 from nitrogen, 6 from each of the 3 oxygens, and 1 from the negative charge. Remember that ground state electron configurations are for neutral atoms, so if the molecule has a net negative charge, there must be 1 extra electron that's not accounted for by either the N or O atoms. Now let's arrange the atoms before we connect them. Again, this takes some intuition, and a good guess is always to put the less electronegative atom in the center, surrounded by the more electronegative ones. For nitrate, that gives us an N surrounded by 3 O's. If I connect each pair with a single bond, I've used 6 electrons and I have 18 remaining. I'll fill in the remaining electrons by adding lone pairs to the terminal O atoms first. This uses up all the remaining 18 electrons. The oxygens all have octets, but nitrogen is still electron deficient with only 6. In situations like this, you need to create a multiple bond to share extra pairs of electrons with the deficient atom. This involves moving a lone pair on one of the oxygens to form a second bond with nitrogen. This is called a double bond because there are 2 shared electron pairs. It allows both O and N to have octets because the 2 shared pairs count for both atoms. The Lewis structure of nitrate is complete once I add a set of brackets and a minus sign to indicate a net negative charge on the molecule. Now pause the video and try writing Lewis structures for CO2 and C2H4. CO2 has 16 valence electrons, and the best starting point has C in the middle because it's less electronegative than O. I need to put 3 pairs on the oxygens to complete their octets, and doing so uses up all 16 of my electrons. Carbon is short 2 pairs, so I need to create 2 double bonds, 1 from each oxygen. Now all atoms have an octet. C2H4 has 12 valence electrons. At first glance, this seems like a harder problem because there's no central atom, but if you remember that H can make only 1 bond, there's really only one choice for the connectivity. The carbons must be in the center, with the hydrogens connected around the perimeter. This arrangement has used up 10 of my 12 electrons, but each carbon still needs another pair. I can accomplish this by sharing the remaining 2 electrons as a double bond between the 2 carbons. So that's it. Don't forget to complete the problem set and read the textbook sections assigned with this video. You should come to class prepared to count valence electrons and draw your own Lewis structures. Thanks for watching.